Hello, everyone. My name is Guo Zhang, and today I'm very happy to talk about our paper at Signal 2021 about consistency and completeness in distributed stream processing with Apache Kafka. This is a joint work with many of my colleagues at Confluent and also our partners from Bloomberg and Expedia. And here's a quick spoiler of my talk. I have to first cover stream processing and its correctness challenges illustrated in Apache Kafka, and then propose our log-based approach to tackle these challenges, focusing on the transactional rise to achieve fault-tolerant consistency, and briefly talk about our other revision-based mechanism to achieve completeness. And finally, I will give a real-world case study of Apache Kafka used in stream processing, and conclude. Okay, let me start with an informal introduction of stream processing. Today, as an important part of the big data landscape, stream processing is considered a different programming paradigm compared to traditional data systems that instead of bring computations in the form of queries to the stored static data, it brings unbounded data in motion to long-lived computations in order to process them asynchronously. And recently, modern stream processing engines have been designed following this principle to provide strong correctness processing guarantees. And among them, Apache Kafka is usually selected as a streaming backbone connecting all kinds of data-driven services and applications. That is because Kafka can store those data streams as highly available, persistent buffers and organize them as immutable logs with logical ordering. So here's a quick concrete example of how stream processing works with Kafka. First of all, stream data is organized as topics, which can be partitioned to achieve data parallelism. New records can be added to the topics as append only, and readers can then fetch them sequentially. A stream processing application could continuously fetch data records from one or more Kafka topics as its input streams, process the records and update states, and generate new records as processing results, append them to the output Kafka topics. When it's done, the processor can commit its input record and then moves on to process the next record from the input streams, and this loop repeats. In the happy path, guaranteeing stream processing correctness is pretty straightforward. However, in practice, failures can happen, and data streams can be delayed, and hence it becomes a much more challenging task to provide accurate processing results. Let's see a couple examples here. First, failures. Imagine that in the above process loop, right before the input record is committed, the process crashed. Then upon recovery, this record will be fetched and processed again because the commit was lost due to failover. And hence, the output records will be emitted twice and the states being updated twice, generating duplicated results. And in practice, because an upstream processor's output can be read as a downstream processor's input, hence forming a streaming pipeline. Such duplicates can also be propagated throughout the pipeline and eventually be emitted to external services reading from the same topology. This is also called the at least once processing semantics. Though I'm using Kafka here to illustrate the scenario, fault-tolerant consistency is a common challenge among all streaming engines. It requires that for each input record, its processing result should only be reflected exactly once, even under failures. In literature, this is also called the exactly once semantics. Now let's talk about another challenge in streaming, time and ordering. Reasoning about time are essential for dealing with unbounded data of varying event time skewness. Here, the event time is usually referring to when a record is created, whereas the processing time refers to when the record is received and processed. In the ideal world, the ordering represented by those two times should be the same. However, in production environment, it is not always the case, because system clocks can be skewed, records can be delayed at their sources or over the wire, and in those cases, there are out-of-order records in the data streams. To illustrate its effects, let's use my favorite example here, the Star Wars film series. Here, the event time represents when each story happened in the Star Wars universe. whereas the processing time is considered as when the story is actually filmed in our lives. If we process them following the processing time order, then at a given time of the processing, for example, here, if we ask, give me an aggregated Star Wars storyline happened so far, we will be generating an incomplete result because of the out-of-order data. As illustrated above, completeness is another important correctness challenge to stream processing, which requires the application to not deliver incomplete results to external services, even with the out-of-order data levels. And in our paper, we presented a log-based approach that Kafka employs to tackle these challenges and pursue correctness guarantees, which is to fully leverage on the persistent and immutable and ordered Kafka logs as both its storage layers as well as its communication channels between distributed processors. Since records sent to Kafka are durable and can be considered as a source of truth, we can have a lightweight transactional mechanism to autonomously and fill over to achieve consistency. And in addition, by relying on upstream emitted records to also be buffered in Kafka logs, we do not need to always block emitting, but can reprocess and revise them when out of data do occur. And hence, we can effectively decouple the handling of consistency and completeness. Those ideas are encapsulated in Kafka Streams, a built-in stream processing library to help Kafka users to build their real-time applications with streaming data stored in Kafka. Streaming applications can be written in the Kafka Streams DSL, and the specified processing logic can then be compiled into a DAG of processors called a processor topology. In terms of distributed processing, Kafka Streams have a tight integration with Kafka's topic partitions. More specifically, the compiled processor topology could be deployed on multiple instances. And each instance could read from a subset of partitions from their input topics and process them with their local states in parallel. In addition, the local state stores of the instances are backed up with other Kafka topics called the changelogs. This is similar to the write-ahead logs in databases, whereas here the changelogs are replicated inside Kafka and hence are highly available. As a result, the changelogs themselves can be viewed as a durable source of truth for the processing states because they can always be restored by replaying the changelogs. Now let's go back to our fault-tolerant consistency. As we illustrated above, a typical streaming application of Kafka involves the following operations in the processing loop: committing the input record as completed, updating the state when processing the record, and finally emitting the results to the output topics. Exactly one semantics requires that all those operations will need to happen automatically. And with Kafka Streams, those operations can be mapped to the following, actually. First, committing on the input streams is implemented as appending records to Kafka's internal offset topic, representing the position of consumers from which they can resume fetching and processing. Second, the state updates are always paired with record appends to their corresponding changelogs as a source of truth. And finally, emitting outputs are just appending records to the downstream output Kafka topics naturally. And hence, we can reduce the atomicity requirement to a bunch of record appends across multiple Kafka topic logs, such as either all of those appends succeed and are visible to the downstream consumers, or none of them do. And to achieve this, Kafka Streams leveraged on a transactional messaging protocol of Kafka. More specifically, we allow producers to append records across those topics in a transaction. And to manage the transaction, on the Kafka brokers, we instantiate a transaction coordinator module, along with a specialized transaction log stored as an internal Kafka topic. Here on the left-hand side, we have a diagram of Streams clients talking to the broker's transaction coordinator. And on the right-hand side, I will show you some code snippets inside Kafka Streams when exactly once is enabled. So when a stream instance starts for the first time, it would first register its embedded producer to the transaction coordinator. Upon receiving the registry request, the coordinator would assign its producer a unique ID and append an entry with this ID to the transaction log, initializing the producer's transaction state in its local cache. Here, the cache is just a materialized view of the transaction log, and we can always be restored by replaying the log in case the transaction coordinator fails over. After that, the stream instance can move on to fetch some records from its input Kafka topic partitions, process them, and which may involve updating the states, and then send some records to both its output and changelog topics. When doing so, stream's producers would first talk to the transaction coordinator again, and by adding a partition request. The coordinator would then add a new entry to the log, updating the transaction's current involved partitions and also its local cache. After that, the producers can send those outgoing records to the corresponding partitions as part of its transaction. Note that at this moment, the transaction is still ongoing, and hence those record appends are not yet determined as succeeded or not. And downstream consumers that are configured as reading committed data only would block on reading them. And similarly, Kafka streams can also commit its position on the input topics by sending those records to the brokers. This will be translated as adding the offset topic partitions to the transaction too. Another transaction log entry will be added and the local cache updated. After that, the offset record could be appended to the offset topic as well. And finally, when the stream decides to commit the current ongoing transaction, it could send a prepare commit request to the transaction coordinator. The coordinator would append a new entry to the transaction log and update its transaction status to prepare commit. At this point, there's no turning back, such that even if the coordinator fails over after that, the new coordinator taking over would still be able to know where it's left by reading through the transaction log and be able to complete the rest of operations to commit this transaction forward. To complete the commit, the coordinator would send a special record called the transaction marker to all of its registered partitions in the current transaction. This marker indicates that all record appends earlier than this marker sent by the same transaction ID can now be considered as committed. And after that, the transaction log is appended again, changing the status to complete commit. At this stage, the producer can start a new transaction. In the other path, when there's any errors happening during the processing, Kafka streams could also abort the current transaction following the same protocol. A prepare abort request will be sent, a new entry will be appended to the transaction log, indicating that the transaction is now doomed to abort. And similarly, the coordinator would append an abort marker to all the registered partitions, indicating that all records appended before this marker by the corresponding producer are now aborted. Downstream consumers can hence skip those records when reading sequentially. After that, the transaction log can be updated again, updating the status to complete abort and ready for the next transaction. As you can see here, by leveraging the transactional protocols, Kafka streams can make sure that all records appended across those partitions are atomic. So when failures happen, for example, on the middle instance here, after it has processed some records and append some results to the output and changelog topics, Kafka streams could trigger a rebalance and migrate the failed tasks to one of the remaining hosts. And upon resuming the task, Kafka streams would reinitialize the transaction status, effectively making the current dangling transaction to be aborted. And then it can rebuild the state by reading the committed changelog records, and also reset its reading position on the input topics from the last succeeded transaction, which would align consistently with the restored state. And from there, it can continue processing. And in our paper, we actually have done some empirical analysis on the overhead of transaction compared to the at least one semantics, as well as with some other peer streaming engines. I'll skip them in this talk. I recommend you to read our paper if you are interested. So far, we have only covered the consistency guarantees. And as for completeness, One simple approach would be to couple it together with consistency handling by deferring the transaction commit until all data up to a certain point has been processed. And again, this requires some synchronization between the upstream and downstream processors to reason about the data completeness, hence maybe more end-to-end latency. However, in Kafka streams, we choose a different optimistic approach as to not try to prevent incompleteness through coordinated blocking, but instead emitting outputs earlier whenever possible and rely on revisions to handle out-of-order data. This again is relying on the persistent Kafka logs used as intra-processor communication channels so that early emitted incomplete results can be effectively overridden by later emitted results. Downstream processors, depending on the stream types, could potentially compensate the early emitted records effects when they receive more updates later. And due to the constraint of this time constraint of this presentation, I would not drill into the details of this approach, and I would highly recommend you to read our full paper if you're interested. Okay, let me switch my gears and present a real-world use case built on top of Kafka streams. Bloomberg's real-time pricing platform takes various input stream sources, such as the market events and external reference data, to detect outliers and generate window aggregates for BI purposes in real time. This is encoded as a Kafka streams application through join and aggregation operators. The processing states are backed up by the changelog topics, which are in turn read by another streams application to build this query serving layer on both latest and historical snapshots. At the moment, Kafka streams have been deployed on 116 cores in this platform, with a total of 2 terabyte data in main memory, processing more than 1 billion market events a day. And because the output of this platform is used for various model pricing tasks, data accuracy comes with very high priorities. Because of that, exactly one semantics is needed to guarantee that no duplicates will be generated from unexpected failovers. Only a small overhead ranging from 6 to 10% depending on the input traffic is observed comparing with at least one mode. And in our paper, we actually have another use case from Expedia that also use Kafka stream exactly one semantics. And if you are interested again, you know where to go and read next. With that, I'd like to conclude my talk with a quick recap. We presented a log-based approach with Apache Kafka to provide correctness guarantees for distributed stream processing applications. Its built-in library called Kafka Streams implements a transactional log protocol to achieve exactly one's consistency with fault tolerance. And also, it decouples the mechanism from completeness handling to allow emitting early output and compensate with out-of-order data. And once again, if you are interested to learn more, please feel free to download and read our paper. Thank you.